Okay, so last time we started to, yeah.
So we're talking about this BMS group, right? I'm just a little curious because I know that like the irreducible representations of like the Poincare group are pretty important in like physics, I guess. I mean, from a mathematical viewpoint, they're really important. But do the irreducible representations from the BMS group ever come into play?
Yeah, so I was going to mention at the end, but I might as well say now. So, I mean, it was a big surprise that the asymptotic symmetric group in presence of gravitational waves, which is what we're going to see just now, is this enlargement of the Poincare group to the infinite dimensional BMS group. And so when this was discovered in the 60s, there was, as Jesus pointed out, a lot of interest in the representation theory of BMS group. And there is actually quite considerable work in the 70s and 80s on the representation theory. And people were very excited because people thought that maybe, in fact, just as the representation of the Poincare group play a fundamental role in particle physics, somehow representation of the BMS group should play a fundamental role also, or maybe even play even more fundamental role. But it turned out not to be the case. This is how things happen. And so there is a lot of very interesting detailed mathematical work on the representation of the BMS group. I can give you the references. They're mostly from London school, but the mathematicians who work on that. Okay, so it's again, I mean, one of those things in physics, you know, why nature is the way it is. We don't know why are there particles which are correspond to representative BMS group, which do not correspond to the representative Poincare group. We will maybe see some indication of why this happens, but let's go on. So we're doing this, last time we were doing this, finished this idea of the universal structure of Scratch. And the universal structure, as we saw, consists of Scra is a manifold, which is 2 from R. So all asymptotically Minkowski spacetime will come with this manifold. It has a metric QAB, which is degenerate. This degenerate direction is NA. And then we also saw that it's such that Ln of QAB equal to 0. This is the divergence free conformal frame, as I said before. We don't have to do this, it's just that the analysis simplifies, and you can always do it. It's like going to a preferred gauge to understand the physics. The physics is all gauge invariant. So these are the conditions that we had. And finally, we had this important scaling freedom. If we go the omega, the conformal factor to go to little omega here, then we're going to conformal freedom that says that first of all, Ln omega then must be equal to 0, and omega should not be equal to anywhere on Scra. And under this freedom, of course, the conformal rescale metric goes to omega squared times GAB. So, and therefore, we are got a conformal freedom in the metric and the normal up here. And so the freedom up here is that QAB and A get rescaled. And so we say that, so that gets rescaled to omega squared times QAB, and so omega to the minus 1A. So we don't really have a preferred degenerate metric and a vector field. We have them up to this conformal rescalings. That's what we have on Scra. And as I drew last time, because Scra is divergence free, it's easiest to think of it as a cylinder. So around here we got S2, and then we got these generators. So these are the NA. And we're going to base space, which we call S. And this, of course, is a topology S2. S2 topology up here. So this is a base space, which let me just call it S. And it's topology S2. And each point up here is a generator. So this generator will define one point, we just project it down. This generator will define another point, etc. And then what we saw was that there is, of course, natural projection mapping from here to here. Any point up here is mapped to the same point. And then under the inverse mapping, so there's also a metric here, Q bar AB. And then under the inverse mapping, if you like, the pullback of Q bar AB to Scra is our degenerate metric QAB. So another way to say it is that because of these two properties, the metric QAB on scri can be projected down and gives us a nice metric of signature plus plus on these two spheres. And again, that metric is unique only up to this conformal rescaling. So this is the universal structure. And so now we're talking about symmetries. So this is a subgroup of diff scri, which preserves the universal structure. So if I have one parameter family of diffeomorphisms, on scri, we have one parameter family of diffeomorphism where lambda is a parameter. Then under these diffeomorphisms, QAB and NA are not necessarily left invariant, but they should be mapped to an equivalent QAB and NA. That is what the symmetry group means. So d lambda, and if I pull back, in the pullback of under d lambda, the pullback of metric QAB. If I make a diffeomorphism, the pullback of the metric QAB, it should just get rescaled by omega squared QAB, and omega, of course, will depend on lambda. So one parameter family of diffeomorphisms means I move a one parameter family, and is generated. Therefore, this such diffeomorphisms are generated by vector field CA. Actually, let's call it BA on scri, because these are the BMS vector fields. Right? If you've got a vector field, then it is an affine parameter, and if you move along a finite distance along the affine parameter, you get a diffeomorphism. That's what we are looking at. And under this diffeomorphism, then the metric QAB is allowed to be rescaled, but then there is a tight binding between the metric and n. The null normal, if the metric is rescaled by this factor, then the null normal must be rescaled by this factor. So the push forward of the null normal should be equal to omega t minus 1 lambda QAB. So this is what should happen. If I make a diffeomorphism, the metric should be left invariant except for a possible rescaling. And if there is a rescaling, then NA, so the normal is just rescaled, it's not changed. So this ruling of scri is preserved. So the diffeomorphism can map the generator to the generator, but it cannot map this one point on the generator to another point on this generator and a second point on the generator to a different generator. It must preserve the generators. This is what it says, that d lambda preserves generator. Integral curves. These integral curves of NA are called generators of scri, and it should preserve these whole generators. Right? That's what this says. The vector field NA must be mapped to vector field NA, and the metric should be this. Okay. Now we are looking at the infinitesimal form, and anytime you want to take the infinitesimal form, we just take d by d lambda of that equation, and then the d by d lambda corresponds to the d derivative. So this equation just in the infinitesimal form just says if this is diffeomorphism is generated by vector field BA. I'm calling it BA because it is going to be the infinitesimal generator of the BMS group. That the B comes from BMS. So this infinitesimal form, then it should be the case that LB of QAB should be equal to 2. So I define alpha on scri as a function of scri, u theta phi. So what we know about here is that this omega must satisfy the Ln of omega equal to 0. That's what we, this conformal freedom has a property that Ln of omega is equal to 0, so it must satisfy that. And I'm going to define d by d lambda of omega lambda, the infinitesimal change, the conformal factor, as at lambda equal to 0, as alpha. Therefore, this alpha function, just like omega, alpha can only depend on theta and phi, or if you like, Ln of alpha equal to 0. So I got a one parameter family of functions, each of which is Lie dragged by n. Therefore, if I take the derivative with respect to that parameter, I get some function and that is also the drag. So this is kind of the infinitesimal version of this omega. If you like, this omega is just given by e to the alpha alpha lambda times or times omega at omega equal to 0, which is in this case just 1. Okay, so the infinitesimal form is going to be equal to 2 times alpha times QAB, and Lb of Na should be equal to minus alpha times Na. So this 2 comes from the fact that it's omega squared, and minus alpha just comes from the fact that if I take the infinitesimal version of this minus 1 gives me minus alpha. So it's very simple. The symmetry vector fields are the ones which just satisfy this condition. That's it. Right? That is going to be the generator of the BMS group. Yeah.
Is it type omega inverse with the push forward of n omega inverse? Is it rho QAB?
Oh, sorry. Yes, it is because. It should preserve. I said the right words. I said it should preserve n, but I wrote something wrong. So please correct me when I write such typos. So Lb of n is equal to minus alpha times n. It doesn't make any sense, right? I mean, right?
Yeah.
It's a vector field, so of course this image should be a vector field, it's not a tensor field. So this is the condition that we need to satisfy, and that's it, right? I mean, at some stage it looks like BMS groups is a complicated mess. It's very simple. It is those diffeomorphisms on scri which satisfy this condition are the generators of the BMS group. Again, the relation between the finite transformations and the d lambda and the infinitesimal transformation is that these finite transformations d lambda, they form the BMS, they form the symmetry group, and I told you last time it's called the Bondi-Mesmer-Sachs group. So these finite transformations, finite diffeomorphisms, they belong to this group, which is called the Bondi-Mesmer-Sachs group. And these vector fields that I got BA on scri, these vector fields are then form the element of the Lie algebra of this BMS group. So let's give this BMS group a name. Let's call it B, and therefore this is going to be the Lie algebra. Let's call it boldface B of this BMS group script B. Now, mathematically, of course, Lie groups and Lie algebras are very well defined in finite dimensions. We're talking about infinite dimensions. So to make it all precise, I should really introduce topology and tell you what's happening on this topological spaces. And that is actually what is done in this representation theory by the mathematicians in London. But I think for our purposes, we will not need that. We'll just proceed as though they were finite dimensional spaces. In other words, we'll just use algebraic properties and not worry about topology of the group up here, because we're not going to need it. For representation theory, you need it, but for our purposes, that will not be necessary. Okay, so that's it. So the elements of the Lie algebra are this. Again, to give the analogy, it is like the Poincare group. The Poincare group is a group of diffeomorphisms on Minkowski spacetime, which preserve the metric. And the Lie algebra is the infinitesimal ones. These are the vector fields, and these vector fields are called the killing vector fields of the metric. So I got the 4 translations and the 6 Lorentz transformations, 3 rotations and 3 boosts. Those vector fields constitute the Lie algebra. Is this all clear? Do you have any questions, particularly physics people? Okay. So now we just have to solve these equations, right? We just have to say, well, what does B? What are the forms of B which solve this equation? So when you get slightly used to understanding the structure of this, the vector fields B, the structure of such equations which determine the vector field B, you realize immediately that it's better to start with some special case to understand what these equations are telling us. So let us consider the special case first. Let's suppose, since I do have a preferred vector field here, why not look at those diffeomorphisms which satisfy these conditions, those infinitesimal BMS symmetries which are along this vector field. I have a vector field already, So I just look at such vector fields. So special case, let's look at B is equal to beta times Na. So let's look at, so let's examine. Are there such, is this, can a BA of this type satisfy these equations? Maybe the answer is no, in which case, we'll do something more sophisticated. But if the answer is yes, then we ask, well, how many B's are there? That's the usual thing that we'll do. So let's understand that this condition up here. So what do these equations imply? So let us take the first equation, Lb of QAB should be equal to 2 alpha times QAB. Let us take this equation. Then this will tell us that in this particular case, it will tell us that Li beta n of QAB should be equal to 2 alpha QAB. And I can expand out what is Li beta. So if you got a vector field and multiply it by function and take the Lie derivative of any tensor field, then the answer is that this is, you can expand this out explicitly, but you can check that the answer is just beta times Li n of QAB plus QAM times, so you take dB of beta, so one index is dummy, that becomes a transpose of dB of beta times the vector field n plus the other index dummy, which is transferred now to beta times n. So you can expand this out explicitly if you like, and then we'll find that this is true. This is of course true for where D is any derivative operator. Beta n QAB is just equal to that for any because Lie derivatives don't care about, I'm assuming it starts in free derivative operator, but it doesn't care which derivative operator I choose. So I got this equation up here. But see what is happening. We already know that Li of QAB is equal to 0. So this term is 0. But you also know that QAB times n is 0. QAM times nn. So this term is 0. QMB times nn. So this term is 0. So immediately we see that this term, Li of beta n, if I choose B to be of this kind, then Li of beta n is 0. But I know that Li of beta n should be equal to 2 alpha times QAB. So what we find is that Li of beta n is 0, but okay, Li of beta n is equal to 2 alpha. Yeah, so that's 2 alpha times QAB, and therefore that this implies that alpha equal to 0. So what it says is that if you have a vector field of this kind, then in fact this alpha is even 0 in that case. So for a BMS vector field BA of the type beta Na, we see that BB of QAB should in fact be equal to 0, and therefore by this equation B should also be 0. But now we again substitute, so this equation we already used, and this equation is what told us that alpha is equal to 0 here. Oops. Okay. Well, this equation is what told us that this alpha is equal to 0. And now the statement is that I still have to use this equation up here. So this is the consequence of alpha equal to 0 is a consequence of this equation. Now we see what this equation tells us. So what we also need that B, and B is just beta times n times Na is equal to minus alpha, but alpha is 0, so this is equal to 0. And so I just expand out this, and that just tells us that in fact Bn of beta is equal to 0. So it's an extremely trivial calculation, but it tells us that therefore, in fact, these equations are completely satisfied if I were to choose B to be equal to beta times Na, something which is proportional to the generators, where the proportionality factor beta is Lie derived by n, is constant. So this just means that BA is equal to beta, which just depends on theta and phi, does not depend on n, times n. So we're going to symmetry. If BA is of this type, then it satisfies this condition, it satisfies this condition, and we're done. So this tells us immediately that, yeah, in fact, BMS group, the group of diffeomorphisms of Scri, which preserve this collection. In other words, it only can conformally rescale the metric, and it conformally rescale n when the rescaling factors are related in this particular way. If I got such diffeomorphism, and if it is generated by vector field, then if I choose a special case of this vector field to be multiple of n, then there are infinitely many solutions. So we found infinitely many infinitesimal BMS symmetries, and these BMS symmetries just satisfy this CA BA is equal to beta times NA, where beta does not depend on u. Beta doesn't change as you go from one value up and down the generator. Along this generator, what changes is a coordinate u, and along this S2, I got the coordinates theta phi. So therefore, in fact, beta is constant up here. So if you like, this beta, in fact, is projects down to the function we just call it beta bar because of a different space, beta bar on the space S that we got, on the space of generators that we got, or if you like, beta is the pullback of beta bar. So this is on Scri, and this is on the space of generators S. So what this is saying is that really, this is just saying that beta is a function of theta and phi. So you can give me a function of theta and phi, arbitrary function of theta phi, and I will be able to generate the BMS symmetry. But notice an important fact up here. Is it okay to use a yellow chalk? No. This doesn't show. Okay. But there's an important fact up here. So supposing you give me a BMS symmetry BA, such that BA is equal to beta times NA. But this refers to a particular conformal frame. What happens if I change the conformal frame? Then BA is of course going to be, the vector field is the same, but NA is going to be equal to, but NA is going to be replaced by the appropriate null the vector field in that, is going to be replaced by the vector field n prime in that conformal frame. So this is just n prime, and therefore beta prime changes. So what is it? It is beta prime times omega to the -1 times NA. But this vector field was of course the same vector field, which in the original conformal frame was just beta times NA. So that tells us that in fact beta prime is equal to omega times NA. So although B is beta times NA, beta is not really a function. In any given conformal frame, if you give me Q and N, then beta is a function. But if I change the conformal frame, then beta changes. So it is said to be, so when this happens, we say that beta has conformal weight. It's like a function, but it does not take numerical values unless you give it more information, and the more information is that of a conformal frame on Scri. So it's called has conformal is a scalar with conformal weight. Weight 1. And A is a vector field with a conformal weight -1, and therefore BA is just a vector, BMS symmetry should not depend on any conformal frame, and therefore beta has a conformal weight +1. Yeah.
Is that a typo? Should NA be beta? Beta prime equals omega beta, right?
Yeah.
In the box.
In the box, beta prime. Thank you. Beta prime is equal to omega beta. Thank you. Beta prime should be equal to omega beta. So it's called a conformal scale. So in fact, the BMS vector fields are of this kind, but because this changes depends on the conformal frame, this also depends on the conformal frame, because the vector field itself should not choose a conformal frame. The vector field, the symmetry does not know a preferred conformal frame. It deals with all the conformal frames democratically. Okay. So these are this subgroup of this Lie algebra. Okay. So these are the vector fields we consider. These vector fields form a Lie algebra. Now what we saw here was that B's are infinitesimal symmetries if they satisfy this condition. It's going to be a very trivial exercise for you to check that if B1 and B2 are such vector fields, then if I take the Lie bracket between them, it's also a vector field which satisfies them. In other words, symmetries form a Lie algebra. When you think about it abstractly, it's more or less obvious because B is generating a diffeomorphism with some property, with this property. B1 is generating a diffeomorphism with some property. B2 is generating a diffeomorphism with the same property. So if I compose the two, right, I'm going to get a diffeomorphism which again preserves this particular property. But it's good for you to check that in fact if two vector fields satisfy this condition, then the Lie bracket also satisfies this condition. But the question is then what about this? B's of this form type. So they in fact, therefore since they are BMS symmetries, they're of course closed under the Lie bracket. So that let's compute it. Lie bracket. So let's take a B1, B2. This Lie bracket is going to be equal to Lie beta 1 of n times beta 2 of n minus. So this is the first vector field. So what is this equal to? So this is going to be equal to B1A, B, dB of B2A minus B. So this is a definition, and I'll just substitute. So if I substitute, I'll just get here beta is beta 1 times NA in P times dB times beta 2 times NP minus 1 and 2 interchanged. But we already know that so when I do this interchanging, the only thing that I find to be non-trivial would be beta 1 times NBDB beta 2 minus beta 2 times NBDB of beta 1 times n. There will be cancellation of the term when NBDB NA and it will be the same, beta 1, beta 2 will just come out. So the only term that will survive and in antisymmetrization is just this term. But we already saw that ln of beta is equal to 0, therefore this is equal to 0, and this is equal to 0, and therefore this of course is 0. So these vector fields commute. So not only are they closed to the Lie bracket, but the Lie algebra is abelian. And these are called generators of super translations, or sometimes they're just called super translations. So strictly speaking, they're generators of they're called generators of super translations up here. And as you would imagine, there are generalizations of the translations in Minkowski space-time. And we're going to see this in a minute, but let's first finish the algebra of the structure of the BMS group up here. So what we have found is that the BMS Lie algebra admits an infinite dimensional abelian sub-Lie algebra, and this we'll call S. So the vector fields of the type beta times NA belong to this S, which is a super translation subalgebra, where Lie of beta is equal to 0. Now, I just want to say that everything here is on scratch, so I don't always put hat. Every equation is on scratch, so every equation should have hat if you like, if you consistently use that notation. Okay, so that's the first conclusion that we drew, that in fact is an abelian sub-Lie algebra. The second thing we find about this is the following. The fact that there is BMS group admits an infinite dimensional abelian sub-Lie algebra, or the BMS group admits an abelian infinite dimensional abelian subgroup, that already tells you that there is a huge enlargement from the Poincare group. And since this is abelian in the translations, in the Poincare group, the abelian subgroup is the translations, so these are the generalizations, and they are called super translations. Okay. So now, what we would like to understand is a little bit more. So now we want to understand other elements of the BMS group, not only of this type. But let us see if in fact these type of elements, super translations, have some nice structure. I mean, they already have nice structure, but in addition to that, how they interact with the general element of the BMS group. So let us suppose now that BA is a general element of the BMS group, or BMS Lie algebra. And let's suppose now that I got an element super translation. So let's suppose that I consider a super translation. And the super translation is going to be, say, beta times NA. So what I would like to know is, what is the commutator between the super translation and the general element of the BMS Lie algebra? How do super translation interact with the general element of the BMS Lie algebra? Okay. So we want to take the B and beta NA. So this is going to be of the type beta times N. Okay. And so this commutator is just Lie B of beta times N. So I could have done this. Over here I expanded out explicitly, just to sort of give you a variety of calculations. But even there, I could have just written down the Lie bracket as Lie B of the Lie derivative of the second vector field by the first vector field. We could have done the same thing over there. We're just doing it in two different ways to see. Okay. So I obtain here, right. So the Lie derivative of this satisfies this condition up here, and then this is therefore equal to Lie B of beta times NA plus beta times Lie B of NA. But any BMS vector field will rescale n by minus alpha times n, so I get here plus minus beta, which comes out, and then the Lie derivative gives me alpha times NA. Therefore, I obtain here Lie B of beta minus beta alpha times NA. So again, we see that the Lie bracket of any of the BMS generator, general BMS generator, with a super translation is again multiple of NA. But we know that Lie bracket between two BMS vector fields is again a BMS vector field. So we know that this is a BMS vector field because This is the homework exercise. We're not showing it in the class. Lie bracket. I mean, we could do it in class. It just takes 5 minutes, but it's good to think through homework, because Lie bracket between any two BMS vector fields is a BMS vector field. Okay, so it's a Lie algebra. Therefore, we know that this object is again a BMS vector field. But we just saw here that if in fact you're going to BMS vector field, let's call it B prime now. And we just saw here that B prime is of the type, in fact, something times NA, so let me call it beta prime times NA. We just saw that it is of this type. And we just work this out and say that if in fact the BMS generator is beta times NA, then that tells us immediately that the Lie derivative of beta is equal to 0. And so you can also work it out explicitly and check that Lie derivative of beta is equal to 0, but the general argument tells us that that must be the case, and B prime A is BMS super translation. So because the Lie bracket between any BMS element, and which does not have to be of the type beta times n, it's just general BMS element which satisfies this condition. Because the Lie bracket is again a multiple of NA, it follows immediately that the Lie bracket is again a super translation. So if I take a Lie bracket between a general element of the BMS Lie algebra and a super translation, I get a BMS super translation. What this means is that it is an ideal. So this is, if in fact the Lie bracket, if you have got a sub Lie algebra, the super translation is a sub Lie algebra, and if it has a property that the Lie bracket between any Lie algebra element with this element is actually is again an element of the sub Lie algebra, right? Then it means that it's more than a sub Lie algebra. Not only is the Lie bracket closed among two super translations, of the type beta 1 times n1 and beta 2 times n2, beta 1 times n and beta 2 times n, but in fact it's closed for any arbitrary elements B, and I don't know what that B is other than B satisfies this condition. So this implies that the super translation form the ideal. And at the level of the group, it just says that you've got always an interplay between the algebra and the groups. If in fact you've got the ideal, that means that the super translation subgroup which just moves you up and down the generator, right, by amount beta, which is independent of u, so it just moves you up and down the generator more or less rigidly along each generator. It's the same displacement, but the displacement can change from one generator to another because beta is a function of theta and phi. So that is the super translations. And what we're showing here is basically that if I take the BMS group and if I quotient it with the super translations, that if I take the full BMS group, then the super translations, they form a normal subgroup. Not only is it an abelian subgroup, but it's a normal subgroup. And the general fact about mathematics, just groups, is that if I give a group and you have to give a subgroup, it doesn't have to be abelian, but if it's a normal subgroup, I can take a quotient, and the quotient is again a group. So this is the kind of a fundamental fact about groups up here, which I just write down now. Thus, super translations form normal subgroup. So the statement is that the level of Lie algebra I can take the quotient of the BMS Lie algebra, which you call B, and the supertranslation Lie algebra. I can take this quotient. This quotient is again a Lie algebra. Again, if this looks abstract, you are all familiar with this many times in the example of the Poincare group. In the case of Poincare group, for the Poincare group, we got the subgroup translations, a 4-dimensional abelian translation subgroup. That is a 4-dimensional abelian translation subgroup, which you all know. This translation over x, y, z, t axis, right? And just constant vector fields along those directions up here. And then this not only is an abelian, but it's a normal subgroup. P is a normal subgroup. At the level of Lie algebra, what this means is just that if I take the commutator between a translation, so this is any translation, and any generator of the Poincare group, so let me call it PA. So any Killing vector field in Minkowski spacetime. A linear combination of translations and boosts. So, if in fact you take any Poincare generator, you know that the commutator between them is again a translation. Right? If I got time translation and if I make a rotation, it is left invariant. If I time translation, I perform a boost, I get another time translation. So, in fact, the translations are actually left invariant. And then if I take the quotient of the Poincare Lie algebra, which is 10-dimensional, it is the algebra of Killing vector fields in Minkowski spacetime that you all know about, inflexible rotations up here. If I take the quotient of Poincare Lie algebra by translations, this is just the Lorentz Lie algebra. And now, so at the level of the group, we can take the Poincare group and we can do the translations subgroup up here, and that is the Lorentz group. This is a 6-dimensional Lorentz group. So now the situation is completely similar. What we have is we have got the B and we have got S, and we again know at this level up here, B and S, again we know there is a Lie algebra. This quotient is Lie algebra. So this quotient, this B is like the Poincare group. Super translations are generalization of the translations. So what we are looking for is the generalization of this Lorentz group up here. And that is what we are looking for. Or of the Lorentz Lie algebra, that's what we are looking at. Any questions? It's straightforward. Okay. So I know that not everybody may have taken group theory courses, but this is kind of a standard beginning of the group theory. And we use this in physics all the time without maybe perhaps explicitly knowing that this is actually a quotient, etc., but that's what it is. Okay. So the question is, what is this Lie algebra? This Lie algebra should be analogous this thing. Okay. So what is the element of the quotient? What is an element of the quotient up here? So what does quotient mean? It means that you take the general vector fields up here right? General BMS vector fields, any vector field in the BMS Lie algebra up here. And you say that two are equivalent to each other if they differ by the denominator. In the case of Poincare group, you would say consider any infinitesimal Poincare transformation and regard two being equivalent if they differ by translation. And then we see that the space of equivalence classes is this Lorentz group. So we've got here B, we've got S. We're going to study the structure of all these things in detail as we're doing explicitly, because it is so much in the literature these days, both in quantum field theory and gravitational radiation a little bit. And so we're going to do it, but at the end of it, you don't need to know all the details, you just need to know the structure. Namely, you just need to know that BMS group is a generalization of the Poincare group, supertranslation is generalization of translations, and then this is what we are trying to find out. This is either a generalization of this Lorentz group, or this will be the generalization of Lorentz group. So we want to know what is it. So supposing you give me this BA, and so we're going to say that BA is equivalent to B prime A if and only BA minus B prime A is a supertranslation. That is to say, BA minus B prime A is of the type, let me put prime here, just easier than B prime A minus BA is equal to supertranslation, and supertranslation were called beta times NA for some beta such that Lie and beta equal to 0. So I think it's easiest to understand pictorially what is happening up here. So basically, you have got a general element B and B prime. And the statement is that I got here B prime minus B. So I got some B prime up here. And let's suppose that I got some vector field B up here. And B is supposed to be equal to beta times n. B prime is supposed to be equal to beta times n plus B. So I'm supposed to add to this B a little bit of n, beta times n. This is beta times n. So if this was B, I'm adding this, and therefore I'm going to get a vector like this. This is a vector I'm going to get, which is B prime. Okay. I'm just adding a little bit of this. Now, because I got this mapping, you all know that I can project vectors. I can pull back forms and I can project vectors. Therefore, I can take this B and I project it. So I will obtain some this B. So let me write B prime in another color. So I project B and I obtain some. So this is the base. This is the base point of the generator that I am taking. I project this vector and I obtain some vector up here. And I project this vector and I'm going to obtain some vector. But remember, the difference between these two vectors is projected to 0 because it's vertical. The difference between this and this is projected to 0, which is another way to say that the projection of these things is the same. So B and B, so this was my projected B. Now it's my base space. I put a bar on it, so I get B bar. And then I find that B and B bar are the same. They're the same because the difference between them projects to 0. Is this clear? Yeah. I got two vectors and difference between them projects to 0. Therefore, if this vector projects to something, this vector must also project to the same thing because the difference between them projects to 0. Okay. Therefore, every vector up here, every BMS vector field, in fact, has a nice projection under this equivalence relation. In other words, this equivalence class of B's this equivalence class under this equivalence that B is equivalent to B prime if the difference is beta times NA. So this equivalence class under this, so this equivalence class means the collection of all these B's, right? All the equivalent B's, I'm putting them together, there's a set of those things. So each of these set is characterized by its projection, by its unambiguous projections on our base space S. And this projection is what we call B bar. So I can have B, B prime, they all differ from each other by super translation, but they have exactly the same projection down here. Therefore, each vector field, each of these equivalence classes, each element of this quotient, so this element of the quotient is these equivalence classes. Element of this quotient up here is this equivalence class up here. So all that is getting projected to a vector field down up there. So we now have characterization of elements of this quotient. In other words, of the analog of the Lorentz-Lie algebra we're looking for, it is just equal to the projection of these vector fields down. What is the condition on this projection B bar up here? Well, this condition trivializes because we're projected, so there is no longer n there anywhere. But this condition says that both B and B prime must satisfy this condition up here. And therefore the statement is that this B bar we have must satisfy that B bar of QAB should be equal to 2 alpha bar of QAB, Q bar AB. QAB projects down to Q bar AB, as we saw in the very beginning, that in fact QAB was here, the pullback of Q bar AB on the base space. Alpha is such that ln of alpha is equal to 0. So alpha is constant along the generators. Therefore alpha also projects down. Therefore these conditions of the BMS vector field, B and B prime and all the vector fields which differ from each other by super translation, they are characterized by B bar, and that B bar satisfies just one condition, namely this. But this condition, you will immediately realize, it says that the Lie derivative of metric Q bar AB is a metric. This is on S, on the two sphere of generators, on the base space up here. And so this is a metric of plus plus signature on the two sphere. And we're just saying that the Lie derivative B bar is proportional to B bar. This is just saying that B bar is a conformal killing vector field. So B bar is a conformal killing vector field on this base space S up here. So this Lie algebra is just the Lie algebra of conformal killing fields on the two sphere, on the metric two sphere. But now it turns out that I just take it as a fact. I mean, again, it will take me 15 minutes to prove it, so I'll just take it as a mathematical fact. It turns out that the Lie algebra of the conformal group, but also at the level of Lie algebra, this Lie algebra, because this S has topology, it has topology S2. Any metric on the two sphere is conformal to a metric on the unit two sphere, round two sphere, x squared plus y squared plus z squared equal to 1, or if you like the metric which is just d theta squared plus I squared theta d phi squared. Any metric on a two sphere is going to be conformal to a round metric. So any metric, every is conformal to a round metric, the metric on the standard or the round two sphere. Any metric is conformal to a round metric on the two sphere. So we're just looking for the conformal group of the standard sphere metric. It's a fact that that conformal group of a two-dimensional round, two-dimensional sphere, in particular also a round two sphere, is isomorphic with the Lorentz group in 4 dimensions. Now, this is a fact. I can prove it. It's a very beautiful fact, but again, it will take us too long from our physics. So let us just understand it. So the statement up here is that this conformal group is isomorphic to, all right, confirm with the algebra, is isomorphic to the Lorentz algebra. So let me summarize the last part in 2 minutes, and then we can go ahead. What we are seeing is that we've got the BMS group and the super translation form an abelian, the ideal. Therefore, I can take the quotient, and I can take the quotient, and I'm asked, quotient is the structure of Lie algebra, and I'm asking, what is it? Then we saw that the element of quotient is equivalence classes of BMS vector fields, where two differ from each other by a multiple of Na. Because two differ from each other by a multiple of Na, they can be projected down. And I obtain a vector field B bar. So each equivalence class, each element of this quotient is just is in one-to-one correspondence to a vector field on the base space. And furthermore, because of this condition, that vector field must be a conformal killing field of the two metric. But on a two-sphere, the conformal structure is very rigid, and the conformal group is just has some structure, and it's a well-known fact. It comes from simple, very beautiful geometry, that is the same. It has to do with light cones in four-dimensional Minkowski space. You can check that the group of the conformal transformations of the group generated by conformal killing vector fields on the two-sphere is the same as a Lorentz group in four-dimensional. So we have answered this question, this Lie algebra, and the question was, what is this equal to? And now we have answered it. We have said that this is also a Lorentz group. So in fact, the structure between the Poincare group and the BMS group is really very parallel. We got a group, we got a group. There's a abelian normal subgroup, abelian normal subgroup. Quotient is again the Lorentz group up here. The big difference is that this is finite dimensional and this is infinite dimensional. So this is what has caused us the enlargement. In Poincare group, the translation subgroup is a four-dimensional abelian subgroup. The BMS group, the super translation subgroup, is an infinite dimensional abelian subgroup. How did this happen? Why did this happen? I mean, of course, it all came from our definition and everything, but it's a little bit abstract in terms of, as Mike was asking me last time, you did conformal completion and all that. I mean, it's all to do with this conformal completion. Can we understand it in the language of physical space-time as to how this came about? And this is our next topic that we'll discuss, not this next Monday. There's no class on this Wednesday, but there's a makeup class will be on Friday, April 13th. So on next Monday, we'll see how did this happen. Well, this happens because of gravitational waves. To me, this is kind of a thrilling and shocking stuff, right? I mean, anybody naively would have thought that, well, wait a minute, I'm talking about asymptotically Minkowski space-time. So the asymptotic symmetry group should be the Poincare group. We find no, it's not a Poincare group, it's an infinite dimensional generalization of the Poincare group. Translations have been generalized to super translation. One would say, wait a minute, but my metric, the physical metric that I got asymptotically flat space-time, I got a physical metric, G hat AB, that goes to the Minkowski metric plus terms of the order of 1 upon R. Surely, when I go to R equal to infinity, the leading order metric is a Minkowski metric, and therefore asymptotic symmetries should be the symmetries of this Minkowski metric. And we all know from our elementary school that the symmetries of Minkowski metric are this Poincare group, right? We know that. So how can it be that this asymptotic symmetry group here is not the Poincare group? What happens is this beautiful subtlety. What happens is that if there are gravitational waves around, then if you give me the physical metric, I cannot single out a canonical Minkowski metric to which the physical metric approaches like 1 upon R. If I find one such metric, right, then Ryan can find another metric, eta prime AB. It's also flat, but it's not true that there is a unique flat metric because the two flat metrics can be related to each other by diffeomorphism. And the statement is that this turns out also, in presence of gravitational radiation, the boundary conditions of G hat AB is eta AB plus O of R of certain kind. And again, this is going to be a homework problem that will be obtained from what you already know, is of a certain kind. And then the statement is that if in fact the physical metric has this fall off, then it's also of the type eta prime AB plus O of 1 upon R. These are flat metrics, both of them are flat metrics, and therefore they are related to each other by diffeomorphism. And yes, they are, but they are related to each other by an angle dependent translation. And this I will explain much more next time. If in fact, if I take eta AB and I just perform a translation on it, then of course I obtain eta AB, I don't change anything. But if I make an angle dependent translation, so for example, x goes to x, y goes to y, z goes to z. This is an example, you can do more general. And t goes to t plus some function of theta phi. Not a constant, but a function of theta phi. So it's an angle dependent time translation that I'm making up here. If I do that, of course this eta is not going to be left invariant, because this is not an isometry, because if this is a constant, then this eta will be left invariant. But then you can check that if I do that, this eta AB just picks up 1 upon R part. And therefore, eta prime AB, for which the Cartesian coordinates are x prime, y prime, z prime, and t prime, this Minkowski metric, for which x, y, z, and t prime are the Cartesian coordinate, is not the same as eta AB, and the two differ from each other to order 1 over r. Okay? And because they differ from each other to order 1 over r, given g prime, I can either expand it like this or I expand it like this. Now what is going to be my asymptotic symmetry of GAB? Well, you could say, well, I can expand it like that, therefore it's a Poincare group of this. Or I can expand it like that, and this is a Poincare group of this, and so on and so forth. So basically, asymptotic symmetries would be the union of the Poincare group associated with eta, eta prime, eta double prime, etc., which are related to each other by angle dependent translation. And that angle dependent translation are the super translation. Remember, super translation was always of the type B. A super translation was always of the type BA is equal to beta, which only depends on theta phi. I'm saying it. I got this angle dependent translation up here. So this enlargement comes about because when there are gravitational waves, to allow for gravitational waves, I have to put some fall-off condition. It cannot be too strong. If I put too strong, then I won't have any gravitational waves. But this weaker fall-off condition is such that if the metric approaches the Minkowski metric plus term of the 1 upon r of the prescribed type, then it also approaches Minkowski metric eta prime plus term order of 1 upon r. And the two differ from each other by angle dependent translations. So I have to add all these Poincare groups. I have to put together all these Poincare groups, and all these Poincare groups, Poincare group of eta, Poincare group of eta prime, etc., they all sit together. That is the PMS group. So to me, it's a very subtle and beautiful thing that presence of gravitational waves don't allow you to have a Poincare group as an asymptotic symmetry group. And this was a shock in the beginning. And I have to say that many people in particle physics, leading or people in particle physics, sort of didn't understand this point until then. I mean, they didn't understand this point. They said, well, it goes to Minkowski metric plus 1 upon r. The symmetric group is a symmetric group of this Poincare group. And the statement is no, it's a bigger group. Okay. So next time we're going to understand this enlargement. What I just sketched here, we're going to understand it systematically, and then you'll see that in fact why it is that the group is enlarged. I mean, basically I told you the argument, but let's do it in some detail. Okay, so see you next Monday.